So good work, everyone, getting here at 8:30 on the last day. I don't think as a student I went to many 8:30 lectures. Yeah, and thanks again for coming to all the lectures, and so thanks so much to Christoph and the other organizers for the huge amount of work in sort of putting on this wonderful summer school. So now that I'm at the last lecture, I should tell you some actual theorems. And so this is just sort of a summary of sort of the notation from last time. Originally, we were thinking of sort of spin systems where, like if it's a coloring, the colors are, say, red, blue, and green. But I wanted to interpret that as a cluster where we were encoding it by messages on sort of edges, where these are now sort of probability distributions. Okay. But it turns out, and for some of the things we want to understand, we do need this sort of complicated cluster model. But it turns out if we're just interested in the question of when there are solutions to the random CSP, we can work with a simplified version of this model. So if we had this boundary condition here, so we could work out what all the BP messages are. So if I encode it as a vector of blue, green, and red, this one only has red children, so it's sort of half-half between blue and green, whereas this one has to be a green, so it's 0, 1, 0, and this one has to be a blue, so it's 1, 0, 0, and then the root has to be a red, so it's 0, 0, 1. But these probabilities, will be important if I want to know how many colorings there are in the cluster. But if I just want to count the number of clusters, it's going to be enough for us to just sort of know, is it a point mass on one of the colors, or is it some other distribution? So I'll write R of UV as a sort of warning propagation message. To mean, so this will take values in just our original set plus another element star, and star is just going to mean we don't know. It's like there's some random. So R from U to V will be equal to A if M from U to V of A equals 1, and star if M from, if let's say the max of A prime of M from U to V is less than 1. So if we're not certain about, if the message is we're not sure, so in this modified warning propagation messages, this one would be a blue message. No, this one would be a green message. This one would be a blue message. This one is star because we don't know. And this sort of passing to this warning propagation commutes with the belief propagation. So R from, so if, say, MUV is equal to, we calculated using the belief propagation equation, so MUI into U. Then RU to V will just be equal to, in the case of colorings, well, can be written as a function of the incoming R's, and where this WP, or warning propagation, is defined as, so it will depend on the model. In the case of coloring, it's, okay, well, what should it be? So if A is a color, what do I need in order to be certain about that the message is definitely A? It means that the incoming messages must be definitely, you know, this one is blue because I knew that this one was definitely green and this one was definitely red. So I need all the other colors to appear among the neighbors. So if all of the other colors minus the set of incoming messages is equal to A, and it's equal to a star if I look at all of the incoming messages, and I just, let's say, maybe minus the star message. If this has size less than or equal to k minus 2, so in other words, that there's at least 2 colors that I'm not completely sure that my neighbors are. So this is like this one, because this one, you know, it could be blue or it could be green. And I guess it's undefined if Ri minus star has size k. If all of the incoming messages are, you know, if I had a vertex here and I had a blue and green and red neighbor, just say, well, there's no way of coloring that. Okay. And okay, so then for this top message, we have a green one and a blue one and a star one. So the star doesn't really matter, and so we're in so the outgoing message must be red, corresponding to the one we calculated before. So this is a simplified definition for a cluster. Just on each directed edge, you have a message which is either I'm definitely some color, or I don't know what color I am, and then they have to satisfy these warning propagation equations, and then that's our you know, a simplified definition for a cluster of colorings. By sort of throwing out the probabilities associated with the BP messages, we can't easily calculate what the you know, what the size of this cluster is. But if I just want to answer the question of are there some colorings, then this is good, because if there's some cluster of colorings, then there should be some colorings. There is a question there of you know, if I give you a solution of these equations, so all of the frozen vertices, I sort of know what colors they are, and they must, you know, there won't be any monochromatic edges. They'll satisfy the rules of colorings. But then I'm left with the question of, you know, some vertices are not determined by that. So, you know, we wouldn't know. This one could be either blue or green. So how do we know we can fill in the free vertices that have stars on them in some way that makes it a valid coloring? And it turns out, well, so that will depend a bit on, or that will depend primarily on how many star vertices you have, how many free ones. if you look, this equation is consistent with everything being a star. So that's just sort of saying, I don't know anything. And that's not a very useful definition for a cluster. So really we want to count clusters that have a pretty low density of these free vertices. And what you can show is that when you're close to the colorability threshold, when D is a little bit smaller than 2k log k, and you can sort of look at vertices, see which ones, run the BP equations, convert those to warning propagation messages, or actually you could just run the warning propagation equations. You can show that the density of stars you'll end up with is pretty low. So I think if, let's say if D is equal to 1 plus beta k log k, approximately, then the density of stars will be about d to the minus beta plus, let's say, something like epsilon k. So it gets fairly small. So we want to look for warning propagation configurations that have a small density of stars. And so this is how you would set the sort of model up for colorings, but you can do the same thing for SAT and for not all equal SAT and other models in this class. And so for SAT and not all equal SAT, these would just take values in true and false and star. Okay, so now with the simplified system, it's almost back in the case of these original spin systems, and so we can write down, what we think the expected number of, or actually we can write down exactly what the expected number of solutions should be. So the corresponding fixed point would be S of R equals. So this is, we've got to think we have D minus 1 children. They each have a warning propagation or a distribution over warning propagation messages on their roots. And then we connect them together and we want to work out what's the distribution at the root of the tree. And because this is a discrete system, it's back to being a sum rather than the integrals that we had for survey propagation. D. Warning propagation. Okay, so you look for a fixed point of these equations, and it's very easy to check that it must be, any solution of this fixed point equation must be symmetric among the colorings, because if you had one coloring that was more likely under S, then when you plug it in here, it would be less likely. It's like if I tell you in one level that blues are more likely than in the next level, blues should be less likely. So if you have equality, then all of the colors should be equally likely. So there's really only one, this is really becomes an equation of one variable, which is the fraction of the stars and the fraction of colors. And so if so that in the fixed point, it will be must be of the form P over K when R is a color, and star, and probability 1 minus P when equals star. Okay, and so you can just plug this in and calculate what the value of P is, and you will get something more or less like this for the, I guess this should be the probability of 1 minus P. Okay, and so then once you know this, then we can get the expected size. So phi of so this first term is saying, okay, you have D children, then you add in a vertex connected to them. How does that change log of the expected number of these warning propagation clusters? And it's basically just when we add a new vertex, will this be compatible with all the neighbors? And it will, as long as you don't have all k different colors appearing among the children. So you want to look, and then the edge term is sort of the same, except it's like, well, R prime, S star of R prime, and this is then checking that you don't have two or the same color on an edge. And there should be a D over 2 there. Okay. And then, okay. So then the one RSB prediction for the colorability threshold. So it should be colorable if and only if phi of D is greater than or equal to 0. So, well, let's say greater than 0. If it's greater than 0, this should say we should have an exponential number of these clusters of colorings. If it's less than 0, we should have no, it should be exponentially likely to find any colorings. If they're equal, then, well, probably that never happens because D is an integer and this is some weird function. So this being equal to having a root that's at an integer, I mean, I don't really know how to rule that out, but if it did happen, by some number theoretic miracle or something, then it should actually be the case that your probability of having a coloring converges to some constant, and it's sort of bounded away from 0 and 1. But okay, I don't think that should be the case. Okay, so and there's a similar, like we can form in a, so I mean this set of, so I can write down the prediction for this in a few lines. It's not like incredibly simple, but it's a fairly simple equation. And I can do the same for the other models, like for not all equal SAT, and SAT is more complicated because it's, so in terms of theorems, we know how, we know for K not all equal SAT, you sort of form the sort of prediction in the same way. Then the satisfiability threshold matches the prediction at least when K is large enough, so bigger than some large constant that was so large that we didn't calculate. I mean, we expect it to happen for all K. It's just many things become easier when sort of K the number of colors or K the clause is bigger. I mean, in the coloring case, you know, this is because, well, like when K is big, we sort of know, like for the coupon collector problem, they're fairly precisely how many colors you need so that you expect all of them to appear among a child. On the other hand, if you have like 3 or 4 coloring, then the probability of seeing all the colors is something you can calculate, but it's not something that's sort of very concentrated. It will just be some number. Okay, so it's a theorem for the not all equal SAT one. The coloring example is still an open problem. So this is the prediction, and so I wanted to mention this and go through it because this is one of the pieces of low-hanging fruit in this theory. So hopefully one of you can solve this, and I'll tell you what's the missing piece. So this is working out the expected number of colorings. You then want to do the second moment method, and to do that, you want to solve the like look at warning propagation configurations where you have a pair of messages on each edge. So you're looking at counting pairs of these configurations. So that corresponds to, so we can do that in exactly the same way. And the messages, so now we're looking for fixed points that are on pairs of messages, R and R prime. And R1 prime up to D minus 1, D minus 1 prime. And then, okay, so product of S2 Ri prime. And then I just want the indicator that warning propagation of the Ri's is equal to R, and warning propagation of the Ri primes is equal to R prime. So it's just, you just want each of the that you have 2 copies, and you each want them to behave like a warning propagation configuration. And so you want to say, what are the fixed points of S's here? So S is a function on k plus 1 squared variables. on the other hand, like when you have sort of not all equal stat, there's the configurations it can take are true, false, and star. So it's like 3 squared or 9 variables. So the reason why this was easier is it's a function of 9, and there's really a symmetry between true and false. So it's really a function of 4 variables. This is maybe a function of k plus 1 variables, k plus 1 squared variables. Okay, but there's a lot of symmetry to it. So there should be 2 types of fixed points. One I'll call the independent copies one, which just says the two copies are independent of each other. So S star here will just be the fixed point we had when we were just looking at one copy of the model. So it just factorizes. There's another one I'll call S identical, R prime. So another way I can make 2 of these colorings is to just have R being one coloring and R prime being exactly the same. So it's just S star of R, indicator that R equals R prime. So there's so the 2 copies are exactly the same, and this is a fixed point of the equations as well, and it's sort of important that this. So if we just had the original coloring model and worked out the BP fixed point, and then looked at the second moment method, then the product one would still be a BP would be a BP fixed point in the pair model, but 2 identical copies would not be a BP fixed point in the pair model, and that's because this is sort of what's special about looking at this cluster model or this warning propagation model. It has a rigidity to it. So if I were to take a coloring down here, okay, we talked about the reconstruction problem. You know, most of the time, or a lot of the time, I can exactly reconstruct, you know, what the root is and lots of other vertices here. But there'll be some vertices that are free, that could be, say, either blue or green. And so for a given boundary condition, I can't be exactly sure of what the root is all of the time. On the other, and because of that, in the pair model, a typical boundary condition won't exactly, if I have the same boundary condition down here in 2 copies, I won't necessarily have exactly the same value at the root. It doesn't have this sort of very strong rigidity property. So, the fixed point of the BP equations will have would be that they're equal a lot of the time, but not all of the time. So when we calculated the second moment method, we got something like this, where there were these little maxima close to 0 and 1, which corresponded to there being clustering. What happens when we, on the other hand, when we move to the cluster model, the picture will look sort of like this. There'll be 0 and 1 will be local maxima. And that's because essentially, if I fix sort of a boundary condition of messages or warning propagation messages. I tell you all the messages at level L, you can just work out and calculate everything else. So the faraway ones, exactly, there's just a single unique way of completing it. So on the, say if we were doing this on the infinite tree, there's no way of changing if you have one valid configuration, there's no way of just changing a finite number of these messages and getting another valid configuration. You have to change infinitely many of them. And so that's sort of a way of thinking about the local behavior. On the graph, the way that manifests is that if you start off with one cluster, you have to change a linear number of colors to get to another valid cluster. Okay. And so when you find these fixed points, just two identical values is another fixed point. Another one that's sort of like this by symmetry would be sort of R an indicator that R equals, I could just permute all the colors. So I take some permutation R and multiply R prime by sigma. So this is a permutation of the colors. So switch blue with green, and then you'll get another valid coloring, and this is also a fixed point. And what I claim is that these are the only BP fixed points, and if you can show that, then you can prove this prediction and exactly determine the number of colorings in a random regular graph. At the moment, the best results are sort of bounds, which restrict it to 2 possible values. But this would sort of nail it down to exactly 1 possible value, unless somehow this phi happened to have a root at an integer point. Okay. So that's, yes?
So how constructive is it? Can you really compute phi of t? If I give you a graph, is it easy to compute phi of t, or?
I mean, this is just a real valued function. So,
but how? That's a big question. But it says colorable if and only if phi of t is greater than 0. So do you have ways of checking this?
So numerically, it seems hard to actually. So this is. So the threshold for this is about 2k log k, and finding a coloring. There are algorithms that say find. I'm not sure about counting colorings, but so okay. If you can't find a coloring, it's pretty hard to count them. And you can't, so the algorithms that we know for finding colorings, in polynomial time, all seem to break at about k log k, which is half the colorability threshold. So, except on fairly small examples, this would be hard to check numerically. Yeah. So you just have to believe the theory. The conjecture. Yeah. Good. Any other questions before I? Yeah.
Is there anything believed to be like a threshold on where good algorithms can exist that coincides with the currents?
Some people. I guess the most widely believed conjecture is that the algorithmic threshold for finding colorings should correspond to the freezing threshold, the point at which if you take the tree and look at level L, that you can exactly reconstruct the root. And what that sort of means is that faraway spins exactly determine what the value at your particular location. And so if you were sort of filling the vertices in one at a time, you can, pretty early on, you can make sort of a fatal mistake where if I set a vertex to blue, but actually the very far away vertices told me green was the only possible answer here. But as I mentioned sort of last time, it's still an open problem as can we show that there's a regime of clustering where you have clusters but not freezing? And then the sort of supplementary question is, if we can prove that exists, which we expect that it does, are there algorithms that sort of work while you have clusters of solutions, but they're not frozen? Good. Any other questions? Okay, so I want to let me tell you a slightly different model where so what about independent sets? Can we? What are the? Let's work out the size of the biggest independent set. And this is one where I'll sort of almost tell you all of the proof. So okay, and again on a random deregular graph. So if we were looking at the hardcore model, the BP messages would be something like so this, you'll notice, is never any fixed point of this will be neither 0 nor 1. So we don't have the same sort of rigidity. Because this is a permissive model. But we're interested in the maximal independent set. So we're sort of interested in saying what happens when lambda goes to infinity. So, now we definitely don't want to compute the expected number of independent sets or the expected partition function, as lambda goes to infinity, because, well, if you have that will be dominated by sort of rare graphs. So as you let lambda go to infinity, most of the contribution would come from essentially bipartite graphs. So if you want to make the biggest independent set on say a regular graph, the best thing would be to have a bipartite graph and you have just 1/2 of it in the independent set. But those graphs should be exponentially rare because of the expansion properties of random regular graphs. Okay, but let me just take this equation and sort of what happens as you let lambda go to infinity. Bless you. So BP of infinity would be, you could just think of this as the indicator of actually, so, okay, I wrote this down the wrong way in my notes. So if any of the mi so if any of the mi equals 1, then we should get lambda times 0, and we'll just get 0. Otherwise, if lambda is huge, then lambda times a constant is over 1 plus lambda times a constant should be basically 1. So if we plug in some messages, unless one of them is 1, we'll get a 1 here. If one of them is 1, we'll get a 0. So it's sort of like, so let me just draw it. So if you have, so if all of the messages down here are 0, then the output should be a 1. But if you have 1 or more 1s, then the output will be 0. Okay. So this is going to be our, and we take the limit, our configurations will be just messages that are either 0 or 1 on each of the directed edges of the graph, and satisfying so R from U to V is equal to the indicator that R of UI into U are all 0. So if all of the incoming messages are 0, then the outgoing message is a 1. If at least one of them is a 1, then the outgoing message is a 0. So what has this got to do with the so independent sets? Well, it turns out that this encodes what we call a locally maximal independent set. So we want to find sort of the biggest independent sets on the graph, or it's sort of like local maxima of independent sets, ones where you can't sort of make some small local changes and get a bigger one. And it turns out that those have a very nice structure. Yeah.
Maximum independent set is not equal to maximum independent set.
Sorry, maximal.
Maximal, like with in the sense of subset, and maximum in the sense of cardinality. No? They are not the same concept.
I want to find the largest set of vertices such that no pair of them have an edge between it. So that's in my graph. So independent sets, a subset of the vertices where you don't have any neighbors between them.
Yes.
And among all the independent sets in the graph, I want to find the size of the biggest one. Okay. That's okay. So at a vertex, there are 3 things that can happen. Either all of its neighbor incoming messages are 0, and then this one I'll call a 1, and it should be in our independent set. Or at least among the incoming messages, there are at least 2 1s, and then I'll call this a 0. But there's also a scenario where it has exactly 1 neighbor where the message is a 1. But then this vertex, if I look at its children, all of these must be a 0. So if we look at this, pair, then all of its the neighbors of the pair are 0, and we could choose one of those to be in the independent set. So we call this one free, and free variables come in pairs. So a locally maximal independent set is sort of an assignment of ones and zeros and frees with the following rules. Ones are only next to zeros. Zeros have to be next to at least, at least two ones, and free variables come in pairs. And the free variables correspond to edges where in both directions you have a one message going between them. And then if I want to build an independent set, then the size of the independent set is, well, what I'd like it to be is the number of ones plus half the number of free variables. So every time I see a 1, I can put that in my independent set. Every time I see a pair of free variables, I can pick one of them. The second one is only going to be true if the free variables are somehow sort of subcritical. If I had, again, I could have just take a perfect matching on my graph, say everything is pairs of free variables, but I can't set half of the vertices in my random regular graph to be free variables. So I have to, again, only look for configurations with a low density of free variables. And here, so we want the number of free to be somehow to be kind of much less than 1 over d. And this will make them subcritical, and then so essentially the trees of free vertices will be like trees with a perfect matching in them. And trees with a perfect matching are exactly the trees in which, or finite trees with a perfect matching are exactly the finite trees where the biggest independent set is exactly half of the vertices. Okay, so we want to count these configurations, and then so again we can do the same operation, write down the belief propagation or survey propagation equations, and if so let me write so we want a distribution S of, so I'll write Q for the density of 1 messages. Messages are either 1 or 0. And then the equation, when we so we have some probability of zeros and ones on each of these edges, and then we add in a new vertex. The probability that all of these messages are 0 will be 1 minus q to the d minus 1 over, well, actually 1 minus d minus 1 plus But actually, this isn't quite what I want to do. This will just count this, like the this will just give me a uniformly chosen, locally maximal independent set, a sort of configuration of these zeros and ones on the edges. But I want to find ones that give me a big independent set. So I want to. So how do we do that? Well, we're optimizing in the space of empirical distribution, so we want to introduce a Lagrange multiplier, which is the same as, want to weight things by lambda to the power of the size of the maximal independent set. So lambda to the number of ones plus half the number of frees. And then if we introduce that weighting, then we'll have an extra factor of lambda here. Okay, but this is just an equation in one variable. The right-hand side is decreasing in Q, so there's a unique solution. So for each lambda, you solve this for Q, and then we want to compute the free energy. So this is what is the effect of adding in one extra vertex minus d over 2, the effect of adding in one extra edge, log of 1 plus q to the d. And then this is the effect of adding in one extra edge. You sort of get if you have two vertices that are both 1 at the root, and then you add in an edge between them, then these become a pair of free variables, and you go from having 2 1s to 2 free variables, and the size of the maximal independent set decreases by 1. So we get a factor of lambda to the minus 1 when that happens. Okay, so this is the free, the exponential growth rate of the expected partition function where we weight by this. The corresponding size of the maximal independent set is the number of free variables. Plus half. And then, so for a fixed lambda, this one is 1 over n log of z lambda, or expected value of z lambda. This one is size of the maximal independent set. So the number of independent sets of that size will be this, but then we need to subtract, remove the contribute. This will be sort of, this term should be sort of 1 over n log of the number of independent sets of this size plus log alpha times log lambda, which is the weight of each of the independent sets. So we have to subtract that off. And so we'll look at phi lambda minus alpha of lambda times log lambda. This should be, this will be the 1 over n log of the expected number of independent sets of size or the alpha lambda. Actually, I mean locally maximal independent sets. So we just take the lambda star equals the maximum lambda such that this is non-negative. So we tune this fugacity lambda to get the biggest size of these 0, 1 free configurations, such that we still have some of them, and then take the biggest one, and then the theorem is that when D is sufficiently big, the maximal independent set on a random deregular graph is n times alpha of lambda star. That's, if you're more careful, you can get the next term, which will be some other constant times log n, and then plus some random fluctuations that are just of order 1 in probability. So the size is actually really tightly concentrated. Okay, and this is what you get by plugging lambda star into this formula. So you can, so there's a relatively simple formula for how big the biggest independent set can be. You just solve this equation for Q, plug it into this formula and this formula, take the biggest lambda that makes this positive, and then plug that lambda back into here, and then that's the density of the independent set. Okay, so again, to do this, you want to do the second moment method. Count the number of pairs of these configurations, and so again, you want to solve the sort of belief propagation model in the pair model. And so now it's an equation in 4 variables, 0, 1 squared. What about F? The number of free variables. So this is so in a configuration, this is the number of ones, and this is the number of free variables. So the size of the independent set you can build is the number of ones plus half the number of free variables. So I guess I'm not.
That's when the second moment method isn't on 0 now.
Okay. Yeah. So it's. Yeah. So I can think of it as either. Okay. Very good question. So you can think of it as either 0, 1, f on each of the vertices, or 0 and 1 on each of the directed edges of the graph. So we can encode each of these configurations like this and vice versa. So this is on messages on the edges, vertices saying that they think they're either 0 or 1, or messages that are either 0, 1 free. And so where, a vertex is free if it has 1 incoming 1, it's a 1 if it has no incoming 1s, and it's a 0 if it has 2 or more incoming 1 messages.
Just to clarify my mind, because I have some doubts. So once I read that maximum independent set is in in the sense of inclusion. So you have a star, for instance, and you put the in the center, and then you have a maximal independent set. But now we are talking about the maximum in the sense of the largest cardinality.
Yes. Yeah, that the largest cardinality. That's right. So if you're
in a star, if you put in the center one, it is a maximal independent set.
not in the sense that I'm talking about. So in my sense, maximal will mean the biggest cardinality. So if your graph is a star, you would choose all the leaves.
Okay.
Yeah, I guess maximal is a flexible word that can be, have depending on the context. Okay. So I'm going to do the optimization in this because it's when we take the pair model, there'll be 4 options rather than 9. So we'll have equations qxy where x and y are either 0 or 1. And essentially the equations will look like axy over where so the only way to have a 1-1 is if all the incoming messages are 0-0. A1, 0. Sorry. And I'm gonna, there's a little something to prove, but I must have checked this. Oh, okay. So I have minus 3 minutes left. So, well, you can write down, it's in the notes. Okay, so you can write down this set of equations, and basically there are, you can find 2 sets of fixed points. One that corresponds to 2 independent copies of locally maximal independent sets, and one that corresponds to 2 identical copies of them. And yeah, essentially this, you solve those equations, show that the biggest contribution comes from 2 independent copies, then the second moment method works. If you're really precise about it, you can sort of understand the lower order term and get sort of that these maximal independent sets are really concentrated. But I should finish off there. So that, yeah, so yeah, thanks for sticking to the end of the lectures, and yeah.